Hello all, thank you for giving me the opportunity to talk in this amazing workshop. Today I will introduce you to the work I do at ICFO in the Institute of Photonic Science in Barcelona, Spain. And I'm going to introduce you to a new technique to measure atomic polarization. And the idea is to use this technique to do micro-bio-magnetic measurements. So these are the topics I will talk about. First of all, I will talk a bit about the state of the art of different magnetic sensors, and I will focus into properties in particular, that are the sensitivity and the spatial resolution. Then I will focus on this new method that is cavity-based and relies on the Pondre-Verhulst technique. And finally, it follows the outlook conclusions and future steps. So let's start with the context and motivation. So when it comes to magnetic sensors, there are two properties that we really care about, that are the sensitivity, the minimum signal we can measure, and the spatial resolution, that is related with the size of the sensor, or equivalently, the sensor characteristic length. And when we plot these two variables, we see that there is a limit on how well we can do it, represented here with this green line. And this is because as we are reducing the sensor size, quantum effects start to be relevant and they limit our sensitivity. And I want to draw your attention to this corner over here, where we have the best sensitivity so far, that is OPMs among squids. And I think at this point, I don't have to convince anyone here why atomic sensors are so promising, but long story short, they are very sensitive, as we can see, they are very versatile, and they are very cheap to produce. However, if we see this plot, we see that no one has miniaturized a sensor more than 1 millimeter sensor characteristic length, which creates a gap for applications where you need high sensitivity and high spatial resolution. So what could we measure with a sensor that works at room temperature and is sub-millimeter or millimeter OPM? Sorry. There are a lot of spoilers. There are a lot of applications from biomagnetism to ultra-low magnetic resonance that works pretty well with microfluidics and lab-on-chip technologies. Also, in fundamental physics, we can find some applications since some dark matter models predict magnetic-like forces. And also in electromagnetism, we cannot invasively measure electronics, batteries, solar cells, and so on. And since this year, WOPM is attached to biomag, I will focus a bit more in biomagnetism, where we can find a lot of organisms that are millimeter size. So one example is this one. In the last year, there were nearly 2,000 papers with C. elegans in the title, that is this 1 millimeter worm. Another example can be found in Drosophila, that is the fruit fly. There were around 3,000 articles, and nearly 4,000 talking about zebrafish, that is the smallest vertebrate system model that you can have. After 24 hours, they have a heart beating, muscles, and a spinal cord. And after 48 hours, they are literally spherical. That is something that physicists tend to like. And if we talk about scaling, the thing is like, will this organism create a significant magnetic field? Let's talk a bit about scaling. So imagine you want to measure the magnetic field of something big, like a human, or in this case, Superman, versus the magnetic field that can generate a supermouse. If we suppose that the magnetic field, the source is localized and is a dipole, the field will be proportional to the magnetic moment over the cube of the distance between the sensor and the source. Also, the magnetic field, we can assume that will be proportional to the volume of the source. And supposing we want to measure an organ like the heart volume will be proportional to the size to the 3. Equivalently, the distance to the heart will be, if we can get super close to the heart, it will be proportional to the size of the source. So if we combine all this together, we can arrive to the conclusion that the field strength has no dependence with size. And this looks like it might be true. One example is that if we look at the magnetocardiogram for a human, it's pretty comparable in strength with the one of a mouse. So we have reasons to believe that the zebrafish magnetocardiogram will be in the order of tens of picotesla. And what we want to do at ICFO is to measure magnetotactic bacteria. So from a physics point of view, these bacteria are self-propelled compass needle. Their magnetic properties are assured due to some nanoparticles they have over here, and here you can see two, that forms a magnetosome that is called. And on top of that, they have the property that they tend to go to areas that are depleted in oxygen. So if we combine these two properties together, they are perfect candidates for cancer treatment, because on the one hand, we can control them by sending different magnetic fields, and on the other hand, they will tend to go to areas that are depleted in oxygen that are usually cancerous cells. So for example, here in figure D, you can see that they are pretty good at their job, and they are attached to some lung cancer cells. So this set of pictures come from the magnetism and magnetic material group in the University of Basque Country in Spain that are our collaborators. They are the ones that are sending us the bacteria. On the right, you can see the image when the bacteria arrive to ICFO using a confocal optical microscope. So how are we going to measure this bacteria signal? Of course, with OPM. Let me introduce you how the OPM we are building works. So first, we have our rubidium cell with atoms that are randomly polarized, but this can change if we optically pump them. So in order to do so, we send circularly polarized light, and we are on resonance with the D1 transition. And after a time, we will reach a thermal state where all of our atoms will be mostly polarized in the F2M2 state. This is the hyperfine picture, but if we take into account that we have buffer gas pressure to avoid the collisions with the walls, we can simplify this picture taking into account just the last electron in the valence band, and therefore we can see that most of the atoms are polarized with spin, electron spin plus 1/2. Once our atoms are polarized in the presence of a magnetic field that is perpendicular to this direction of polarization, our atoms will start precessing with a frequency that will be proportional to this magnetic field. And the constant of proportion in this case is the gyromagnetic ratio, that in my case is 7 Hertz per nanotesla. So now what we need to send is probe light to collect information about these oscillations. And in my case, the probe is going to be also circularly polarized light. And after the atomic interaction, we will see that the light will gain a phase. And by measuring this phase, we will have information about the Lamor precession and the electronic spin. In OPMs, usually the longer the interaction between atoms and light, the better. That's why in literature, we can find multipath cell configurations. However, this kind of technology gets challenging when reducing the atomic sensor. That's why what we propose is a cavity. So here on the top, you can see the direction we want to go, where we will have our atomic cell, and instead of using mirrors, we will use some coating that will be with high reflectivity for the probe. This is a prototype of the cell that was done as part of the Maximal project, whose interaction length is about 200 micrometers. So again, this is the direction we want to go, but for now we are here, where we are using microscopic mirrors and a cell whose interaction length is 1.5 millimeter. However, the physics we are going to show here are going to be the same for both cases. I don't know what is going on. Sorry. Oh my God. I don't know why I skipped to the end of the slide, so don't look, these are spoilers. Okay. So also something you need to take into account is that when you miniaturize your sensor, you will have more frequently collisions with the walls. And in order to avoid that, you use more buffer gas. And this what we'll do is to broaden your optical absorption, and therefore you will reduce the optical depth. Another advantage of using the cavity is that we will have high optical depth because we will have more interaction light atoms. And also, as we are having a cavity, we are having different cavity modes. So if we choose one that is far enough from atomic resonance, this creates a perfect scenario, these two properties, where we can employ a quantum non-demolition measurement, where the uncertainty of our measure observable won't increase during its evolution. In this case, the measure observable is the electronic spin. So the idea in the long term, in the future, is that this technique could be compatible with spin squeezing to beat atomic noise. So let's talk about this technique. This is how the setup looks like in real life. And if we break it into pieces, we see that we have two different lasers, the probe at 780 and the pump laser at 795, that both lasers will be fiber coupled, and they will be sent to the cavity where we find the cell among the mirrors. And now the combination of the PBS with the quarter wave plate will allow us to collect the reflection from the cavity, and this will be sent to our photodetector. And it will go to the Pondre-Verhulst circuit that I will talk more about in the next slide, but the idea is to use this circuit to measure changes in the refractive index of the cavity due to atomic polarization. And at the output of this circuit, we get the error signal that looks like this when scanning the probe frequency. And this signal will be sent to our FPGA, red pitaya, and the PID output, this will act as PID controller, the PID output will be sent to the laser diode current of the probe laser. So we want to measure changes in the phase of the light due to atomic polarization. In order to be able to detect these changes in the phase, what we are going to do is modulate the phase of the light. So we will use an electro-optical modulator that will operate at the modulation frequency capital omega. This will create sidebands below and above the central frequency of the laser. And then this phase modulation will be converted into an amplitude modulation when the light reaches the cavity. This is because, depending on the frequency we are, the reflected intensity will be one or another. For example, if we are on resonance, the reflected intensity is minimum. Then the light will be collected with this photodetector and will be demodulated using a frequency mixer, and the signal we send to the electro-optical modulator. And after a low-pass filter, we get the famous error signal. And let me distinguish here two different cases. One is the slow modulation case, where the modulation frequency is smaller than the cavity line width, and the error signal looks like this. And we have also a fast modulation case when the opposite is true, and we can distinguish the sidebands. So in principle, you want to be in this regime, since your slope is steep, and therefore a small change in phase gets translated into a big change in the error signal. However, now we are in this regime, since the cavity line width is wide, since we have atomic absorption, and the modulation frequency is around 100 megahertz. So when we have this idea of using Pondre-Verhulst to measure atomic polarization, we saw that it was something that no one did before so far. That's why we needed to create a model that will combine atomic vapor optical properties with optical cavities containing a dispersive media. You can read more about this in this paper. And to validate the model, what we used was the transmission peaks. So what you see here in gray are the experimental transmission peaks. And what you see with a dashed line is a fitting with our model, where these are fixed parameters that are the atomic length, the cavity length, the number density, the window transmission of the cell, reflectivity and transmission, and the amount of buffer gas. So we will fit using this formula over here, when again we have the transmission through the mirrors, transmission through the window, that will be a complex number with a modulus and a phase, as you can see here. And of course, the modes will be separated by a free spectral range. And the important thing is here. So in red is plot the atomic absorption spectrum that is where we have the atomic contribution that will depend on the refractive index. And the refractive index will depend on the electronic spin. So here is the case. Here is how we can measure the electronic spin. And of course, in this formula, gamma 2 is the full width half maximum of the absorption spectrum. Let's have a look now at the error signal. Of course, it will depend on the reflection from the cavity. And again, here we have our atomic contribution that again will depend on the refractive index, and again depends on the electronic spin. And that's why this error signal is sensitive to changes in the refractive index of the cavity, and also is sensitive to changes in the electronic spin. So we will use it for the detection of atomic polarization. And also, on top of that, we will use it for laser frequency stabilization to the cavity. Okay, so what happens now when we pump our atoms? What we see experimentally is a shift of the error signal to the left or to the right, depending on how we are polarizing. So this shift will be proportional to the real part of the refractive index when there is polarization minus when there is no polarization. And in this formula, we can see that depending if we are pumping with sigma plus or sigma minus, we will polarize to plus 1/2 or minus 1/2. And that's how we can explain the shift to the left or to the right. Also, other thing we did was to measure this shift for different probe frequencies. And what we got was the dispersive profile centered around the atomic resonance. 4 different degrees of polarization. So what we were changing here was the pump power. And we can see in red for 0.29 degree of polarization, 0.57, 0.82. In this publication, we also prove that this method can be quantum shot noise limit. But before going there, let me explain you what is going on this slide. So here, what we are doing is we are not scanning the probe frequency anymore. And the modulation frequency, we change it to 19 megahertz. And we are going to pump our atoms sinusoidally with an amplitude of 1 milliwatt and a frequency of 1 kilohertz. So before the demodulation, after the amplifier, what we are going to see are psi bands due to this modulation of the refractive index, 1 kilohertz apart. This is before the demodulation. After the demodulation, we will see our peak at 1 kilohertz. And we did the same for a signal of 30 milliwatts, and we see our peak and the different harmonics. And after the demodulation, we see again our signal at 1 kilohertz. We wanted to go to a regime where the signal is small and big, so we can show that we can measure a big range of polarizations that will be interesting for magnetometry later. And if we look at this spectrum over here, we can see why I said that we are quantum shot noise limited, because here in yellow, we have the laser off with just electronic noise. And when we turn on the laser, we see this offset, and we don't and then we stop pumping, and we record the free induction decay. And this free induction decay will follow the behavior of a damp oscillator, where our atoms are precessing at the Lamour frequency, and we have here an envelope that is exponential due to different relaxation mechanisms that are indicated by this coherence time T2. So what we did in the lab was to record a train of FID signals with these 2 steps and an additional one for the heater. This was done by using a PID controller by looking at the 0 crossing points. Then what we did was to feed these signals with the formula I showed you before, and we will get a Lamour frequency per 600 microseconds. Then we convert to magnetic units using the gyromagnetic ratio, and we will have a plot of magnetic field versus time. If we Fourier transform that, we get our sensitivity plot that looks like something like this for a acquisition time of 16 seconds, where we have, for high frequencies, a noise floor of 30 picotesla per square root hertz, and for low frequencies, 38 picotesla per square root hertz. Depending on your application, you will want to go to one regime or to another. And also, this is the sensitivity we measure, but as I said before, we are expecting to go to the fast modulation regime, and that will give us an improvement in the sensitivity by a factor 10. So we will expect a sensitivity of 3 picotesla per square root hertz. So what do we want to do with this magnetometer? We want to measure the bacteria signal. And the idea is to do relaxometry. This is done by applying a very strong magnetic field, so the bacteria gets polarized, and then you disable this magnetic field, and you measure how much time it takes for the bacteria to unpolarize, and it follows an exponential. This is something that has been done previously with squids, and you can find the reference here. And as you can see, it's a measurement that takes a lot of time. That's why we will be interested in low frequency signal. We will be sensitive enough to measure the bacteria signal. Well, it looks like yes. If we go to this reference, we see that they have a sensitivity of 55 picotesla per square root hertz, when in my case it's around 38, at the expense of having a worse spatial resolution. But as I said before, the idea is to reduce the size sensor even more in the future. So let's talk about how we get the bacteria signal experimentally. So the setup in real life looks like this, where we 3D printed this structure that if we zoom in this solution, we have our bacteria, and around it, of around 12 millitesla. We wanted to apply a strong magnetic field because on the one hand, the bacteria will tend to polarize due to magnetic forces, but on the other hand, it will tend to unpolarize due to Brownian motion. So we wanted to apply a magnetic field that is strong enough so we are sure that the bacteria is polarized. regarding the experimental sequence, what we did is the DC field will be always on, creating a magnetic field of 15 microtesla, so we can always have an FID signal. And then we will polarize the bacteria with the polarizing coil for 40 seconds. That is more than enough time, so the bacteria is polarized. Then we start the acquisition, and we switch off this polarizing field. And what we got is what I hope, I'm not completely sure, but it looks like, is the bacteria signal. Here in the OPM, this is what we got. In blue, you see the raw data, and in red is a fitting with an exponential decay. So if we have a look at the fitting parameters, this is what we got: an amplitude of 1 nanotesla, a coherence time of 3.3 seconds, and if we suppose that the bacteria is a dipole and is localized, this is the magnetic field it will generate, being this the number of bacteria, that in our case is around 10 to the 8. And this is the distance between the bacteria and the sensor, that in our case is 16 millimeters. If we compare the magnetic field expected that the bacteria will generate with the magnetic field we measure, we get a magnetic moment of this amount that is a value that is comparable to the values you can find in literature. And then regarding the decay time, what does the theory says? Well, this will depend on Brownian motion, so we have a dependence with temperature. And here alpha is a geometric factor that will depend, if we assume that the bacteria is a cylinder, it will depend on the diameter and the length, that in our case, the bacteria is around 3.5 micrometers. And if we combine all this together, we arrive to a coherence time of 438 seconds, when experimentally we get 3.3, that is more or less in the same order of magnitude. What are next steps? Well, we are working on a new design that will allow us to get closer to the bacteria. So we have here this disc where we can inject the bacteria solution from here. And this is how it looks like in real life. So we have the cavity. Here we have the atomic cell. We have a layer of aerogel for thermal isolation because the bacteria doesn't like hot temperatures. And we have here our 1 millimeter thick disc. So if I move on with the conclusions, if we come back to the map I showed you first at the beginning, we have here a new sensor that relies on a new non-destructive method to monitor the electronic spin polarization and is comparable to other technologies we can find. And the long-term vision, as I said, is to reduce the cell and go to 100 micrometers atomic length. And also, following this direction, we want to get even closer to the bacteria. For this, it will help to have some coating mirrors instead of microscopic mirrors. And also, a design we are considering is to create different cavities, so we can employ a radiometer configuration. And finally, as I said, this method is compatible with a quantum non-demolition measurement. So in the future, we could go even beyond the standard quantum limit if everything goes good. And finally, I would like to thank the Atomic Quantum Optic Group at ICFO for all their help and support, especially to Morgan Mitchell here next to me. And with this, I thank you for your attention, and I'm open to your questions. Thank you.